Hello, Michael.
Hello, Matt.
So we're going to look at applications of exponentials and logarithms.
And that's really important because they come up in so many places. Can you think of a few?
Yeah, we're going to look at a few. So one is nuclear fission.
So like the nuclear bombs.
Yeah, the neutron bonks two neutrons, which bonk four, and the whole thing explodes in a rapid reaction. How about another one?
Finance.
Finance. We were talking about the world's first trillionaire. How did he do that? Exponentials and logs.
Mostly exponentials for him.
Okay, another one.
Well, one we talked about a lot recently is the spread of disease. For instance,
Oh,
COVID, how quickly it spreads.
These are all growth processes. Now, what about the opposite?
Well, how about something like, nuclear decay?
Okay, radioactive decay. Sounds good.
So you often hear about things like so-and-so has a half-life of so many years.
57 million years, right?
Yes. This is how long it takes something to decay into half of what's left over. These are all great examples.
So I think that's enough. And we should look at how we can start this connecting to what we know. And it really comes down to writing down the equation that we want to look at. And should we use, what are we going to use for the growth?
Well, let's use fission. So that's kind of a neat idea. You mentioned it like you have one neutron and it hits some atoms, and then you have two neutrons. Then you have how many?
4, 8, and so on. So it's power of 2.
Powers of 2, right? So you can take 2 and raise it to a power, 2 to the n. And we should think about that, 2 to the power n. Okay, so we want to talk about exponentials, and we're talking about this x function, right?
Right.
So what's the connection between 2 to the n and an exponential? One way to think about it is you can think about this as 2 times 2 times 2 times 2.
N
times, okay?
Yeah.
Times, right?
Right. Now we could use our log formula.
So if I take the log of 2 to the n, this is the same thing as the log of a product of a bunch of things,
which we've already looked at, converted to a sum of logs. Now,
so this becomes, each of those products becomes a sum. So log 2 plus log 2 plus, and again, there's n times, right?
yeah.
So I can simplify that to n times log 2, right? So log of 2 to the n is equal to n times log 2.
Well, let's take this further. What if you're not doing things in multiples of days or seconds or years or whatever? So
what if you have a fraction there, for instance?
Let's do a fraction.
Okay, so let's do a similar thing. So maybe I have an n divided by m. Okay, and I can do the same sort of trick. This is
well, it's n, the 2 to the n is up there, and there's 1 over m's there.
Right, so I can write this as
2 to the n to the power 1 over m.
Maybe I do this, Matt. How about if I take this? 2 to the n, I'm going to get rid of this. 2 to the m over m times 2 to the n over m times 2 to the n over m.
M times.
M times now, right?
Yeah, and m is an integer, so we're okay with that.
So m times.
Right.
Okay. Take logs of both sides.
Yeah.
Log of 2 to the n. Same trick here. I've got m things added up.
So we're going to get that.
So I'm going to get an m here times the log of 2 to the n over m. And this guy we had a formula for. This is n times the log of 2.
Right.
So if I bring the m over to the other side, I have n divided by m times the log of 2 is equal to the log of 2 to the m.
And
Did
over
I-
m.
Yeah. For
N
some
over
reason
m.
I wrote m, but I need n over m, right?
Oh, so now
So
we,
that's the connection between how things grow with logs.
and this could be greater than 1, less than 1, whatever. These are both
Integers.
integers. So
Yep.
that's great. Well, so n over m is obviously a fraction, but what if n over m was pi? Would you care?
Well, you know, pi is very close to a fraction like 27 over 22 over 7, or there's other things like 3.14151.
Whatever it is,
626,
yeah.
you know, so you can write down a fraction, which would give you a very good approximation. So you can just say, by continuity, it's going to hold for all numbers. So log of 2 to the power t is t times the log of 2. That's a very ugly looking t, but that is a t.
Okay, so this is, if this is a positive number, that's going to be growth. And if it's a negative number, it's going to be decay. And so now, how can we use this result to look at these growth and decay applications? So I think we'll need another blackboard. What do you think?
I think we do, but can I, let's write down this formula, because this is such a pretty formula. T times the log of 2 is equal to log of 2 to the t. That way we can erase all the other work we did.
Right, and keep these, and then we'll have
erase them.
space here. And the log, of course, understanding that it refers to the log associated with rectangular hyperbolas,
Right.
which is log to the base e.
So if we look at this, you know, you're reminding me of the exponential function. The exponential function cancels the log. So if I take the exponential of this side, the log goes away, and I get 2 to the t is equal to the exponential of t times the log of 2. Isn't that a nice formula?
Yes, and it's even nicer because we can expand this out. So we can get a direct function of exponential of t with an appropriate scale to get us 2
2 to the t.
So
And that's what we'll use in all these things
that's
here.
what we use in all those things. So let's have our little break and continue after an erase.
Okay.
Well, Michael, we have these wonderful applications. We have this relationship with t and 2 to the power t. So let's think about an application of radioactive decay in the medical field.
Okay, so this is something that comes up quite often if you've ever had a medical scan like MRIs or CAT scans and stuff. Sometimes they put a radioactive dye in you. One that they've used on me is called technetium, and it has what's called a half-life of 6 hours. Do you know what that means, a half-life?
I think it means that after 6 hours, the amount of radioactivity is reduced by a half. So the thing is emitted half of its radioactive energy in that time of 6 hours.
That's right. So if you have a chunk of technetium in your body at time 0, let's say it could be like a gram. Maybe they put a whole bunch in a gram, okay? After 6 hours, you're going to have exactly half that amount.
Yeah, the other half went into the actual energetic particles.
That's right. It transmuted
split
into
into
something
other-
else and went away, basically.
and
Right?
actually created energy.
So after 12 hours, you might think, oh, it went from a 1 to a half, should go to 0. It doesn't go to 0. It goes to half of a half,
Which is a quarter.
quarter, right? And then after 18 hours, what would it be?
An eighth.
1/8. So basically, the formula would be something you had 2 raised to the power, say t, measured in hours, divided by 6 times a. That's how much is
Except
that.
it should be minus, shouldn't it?
It should be minus, exactly right. So I want the reciprocal of 2, so I want a minus t over 6. So this is the formula for how much a as a function of t there is.
Yeah, that's
So the initial amount
And that works, right? Because when t is 6, it's 2 to the minus 1, which is a half. T is 12, it's 2 to the minus 2, and so on. So there we go.
Right. Now, I like this formula. To me, I can see so clearly what's happening. Here's the half-life, the 6. I know it's not a half-life, instead of a double life because of the minus sign. And the initial amount is this a sub 0.
And that's exactly what your little mini table says.
Now, mathematicians often like to write this using their exponential function. So you can write this exponential. I'm going to replace this t by this minus 6 over t, minus t over 6 times logarithm of 2 times a0. Let me ask you honestly, Matt, do you like this formula or do you like this formula?
This one makes perfect sense.
I
This
agree.
one changes basically the base to
Changes
a
the
power
base.
of 2 to the power we used in for x.
And that's one of the little tricks you'll learn about exponentials and logarithms is you can take logarithms base 2 or logarithms base 10, or you can use this logarithm, which we say is logarithm base e, and use them for different purposes. This formula is easy to understand. You see that there's a half-life involved. The length of the half-life comes from the 6, which is our 6 hours. Actually 6.066 hours, if you really want to be precise. But it's a natural thing.
So if it was not technetium but something else, instead of 6, we would put T, capital T here, right?
So for instance, plutonium, which we know is what's produced in nuclear reactors.
That's a long time.
It's 100 million years or something like that.
On a scale using years. So
Years,
T
yeah.
would be measured in years.
That's right. Here we're measuring T in hours, and so we get 6 hours. Of
Yeah, it
water
has
there.
to be that way because the units have to be consistent because we can't take exponential of hours.
That's right. That would
So
make
can
any
we
sense at
write
all.
this in any other way or is that it?
Well, there's something else we can notice is this is a function of T. Here we have an exponential of a function of T. This is just T times a constant. So chain rule, the derivative of this guy is going to be this exponential comes back. Then it's multiplied by, okay, this is, if this was just T, this derivative would be 1.
Right.
Instead, it's T multiplied by this constant, it's minus the 6 times log 2.
Minus 6 log 2.
So I get minus log 2 over 6, all times this a0. And what we notice is a0 times the exponential is the original thing, so I get this nice little formula. Minus log 2
Over 6.
over 6 times a of t. And this is the constant that tells us how quickly things are decaying.
Oh, fantastic. And so this is really nice because all formulas have this natural way of expressing their growth rate, or in this case, growth
decay.
loss. And so the only difference between decay and these other applications, which are growth, basically, is the minus sign is going to go to a plus sign.
Right.
And there'll be maybe some other scale factors, but the principle is wonderfully done here, and we're only using this intuitive idea of powers of 2, and we've applied it to the case of radio scanning using an object whose decay time to half is 6 hours.
That's right.
Good job.
Thank you, Matt.